Do you know where it is? Is it recording? Okay. I will attempt to put this on my... There we go. I'll begin with a word of prayer. So, Dearly Father, we thank you for this day. We thank you for the break, which is again about to start. Help us to enjoy it. Help it to last long. With no snow, but help it last a long time. It seemed like a long time. And I just thank you, Lord, for all your many blessings to us. Help us to use this time today, Lord, wisely. In my prayer, Lord Jesus. Amen. All right, so, yes, the Easter Monday, which is an interesting convention we have here, I guess. But I have to say that out loud to remind myself that we don't have class Monday. Every once in a while I'll make a syllabus that pretends that we do, and then that creates all kinds of problems. So I do intend to give you your test back at the end of class, but I will not give it to you now because that will distract you, of course. So what's the third part of linear algebra about? I have the attendance sheet here somewhere if I can find it. Here we go. If you can add yet another column to this. I'm about to run out of paper here pretty soon, but so we're about to study, I would say in some sense we're going to look at structure and application of linear algebra at this point. Let me try to explain what I mean by that. Application is somewhat self-explanatory. I mean, we'll spend a fair amount of time looking at eigenvectors, which have tremendous use in all kinds of application, solving differential equations, analyzing all kinds of different things. Eigenvectors just come up all over the place. But then we'll also spend some amount of time studying sort of the more general idea of a dot product, called an inner product, and how perpendicularity generalizes to this notion of orthogonality, and the idea of orthogonal complements. This leads to things like, for example, linear regression is something that stems from this. But then we also are looking at structure. In particular, we're trying to understand more deeply what is a linear transformation and what does it look like. Now, up to this point, we've already given an answer to that question, right? Let me summarize what we've learned so far. What we've learned so far is essentially that if you have a linear transformation from a vector space V to a vector space W, right? And the essential result that we found was that if you give this a basis beta and you give this a basis gamma, then we can choose beta and gamma such that what? Such that the matrix of T with respect to beta gamma is just equal to the identity matrix, let's say I, and the size of it is, it's the rank of T, right? That's too much to write there. Let me say IP, 0, 0, 0, where P is equal to the rank of T. In other words, the dimension of the range, right? So what this says is, in some sense, there's a system of coordinates that we can pick for the vector space V and a system of coordinates I can pick for the vector space W such that essentially every linear transformation becomes the following. We just go T of x1, x2, xn equals to x1, x2, xp, and then zeros. That's what that theorem says when you write it in terms of a coordinate system. Any linear transformation amounts to this. I mean, we could also have that it's all zeros, right? And so how do you decide whether or not two linear transformations are really the same transformation? All you got to do, the same transformation, all you have to do is, well, basically pick a basis for V, pick a basis for W, row reduce the matrix, calculate the rank, and then you know whether two given transformations are more or less the same thing. Now, but you see, this is not, I mean, fine, it's true that this is a theorem that we've talked about actually a fair amount. Maybe in specific examples more than this general idea, but moving past this point, when we study the structure of a linear transformation, we're a little bit different. We're going to start asking the question, if I have a linear transformation from the vector space to itself, so this kind of thing is called an endomorphism. Endomorphism of V. Endomorphism is just a fancy word for saying a linear transformation from a vector space to itself. This does not assume any kind of invertibility or anything. The zero map's an endomorphism. All right. The identity map's an endomorphism of a vector space. You always got those two. You can scalar multiply. I mean, there's an easy way to create. Okay, so anyway, the point is, then the question becomes, so if I've got two endomorphisms of a vector space, suppose I've got T, and suppose I've got another endomorphism S, also a linear transformation from V to V, right? Then the question is, well, when are these the same endomorphism, right? Now, of course, we could judge the sameness by using the result that I have above the line. We could just calculate the image of the maps, and we could judge by that. And that would be one way we could do it. We could see, you know, what's the size of the range. If the size of the range was the same, in some sense they're the same. But actually, we can cut it more finely. We can say, well, we're going to insist on using the same basis here and here, right? And so if we study the matrix of T and the matrix of S with respect to the basis beta, using beta for both the domain and the codomain, all right? Then the question becomes, you know, how can I judge whether they're this? Well, if they're the same transformation, right, there's got to exist some kind of basis where maybe that's too strong. That's probably too strong. I think that implies equality. Maybe I should say that there exists a basis beta and a different basis gamma, such that they have the same matrix with respect to. I mean, there's some. If I could pick the right coordinate system with respect to T, and if I pick the right coordinate with respect to S, I can make them behave the same. All right. I still haven't, I don't think, described this notion of sameness as well as I want to. But the question is, I mean, this is. You see, I have reduced the amount of freedom we have. Now I'm saying we have to choose the basis in the codomain the same as I choose the basis in the domain. That's much more restrictive, right? A lot of the way that we created this identity matrix was based on separately playing a game with the domain basis and then playing a different game with the range basis, right? So if we're forcing ourselves to keep the same basis here and here, that's much more restrictive, all right? Now, after a while, we'll eventually learn that, in fact, we can judge whether two linear transformations, in fact, are the same. And so this, well, you guys know, this is what? If I put this in the beta basis, what would this look like? Something like P S beta beta, right? P. One of these has got an inverse. I forget which. It depends on which P it is. I'll just put the P inverse here. But there's a coordinate change matrix, right? And since we're using the same basis in the domain and the codomain, coordinate change is a similarity transformation. So in fact, the question of whether or not two linear transformations are in some sense the same transformation, the same endomorphism of a vector space, amounts to the question is the matrix of T and the matrix of S, are they in fact similar matrices? Okay. So judging the sameness of two transformations is basically, the question is, do they have a matrix which is similar? Right. And so, likewise, we're interested in the question, given A and B in, n by n matrices over a field, when does there exist P in what's called GL and F. So what this is this is invertible n by n matrices over F. Which is, by the way, not a vector space. I mean, the sum of invertible transformations is not invertible. Some of you know what I'm talking about. All right. Anyway, so given two n by n matrices, when does there exist a P, an invertible matrix, such that what? B is equal to P inverse AP, right? So here's the difference. Up here, the corresponding matrix question, A is matrix congruent to B if the rank of A equals the rank of B, supposing that they have the same size. Right? This right here, this says A is similar to B. And here A and B are not matrices of any old size, they're square matrices. So the question we're beginning to ask is, when are two matrices similar? How can we judge whether two matrices, given a matrix A, given a matrix B, how can you decide whether or not there exists a P, right, which similarity transforms one to the other? That is the same question, essentially, as the question given two endomorphisms. How do you judge whether or not they're the same endomorphism in disguise, right? Okay, so that's the big picture of the structure question we're asking. The ultimate answer to this is given to us by something called the Jordan form and the real Jordan form. All right, we'll get to that eventually. But it's a long story to actually get to the end of that story. But the nice thing is that story isn't just a pure abstract linear algebra discussion, even though that alone would be, I think, enough for me to discuss it. The classification, the deciding when A and B are similar, actually brings to bear tools which solve all kinds of real-world problems, namely eigenvectors, generalized eigenvectors. Right? The story of orthogonal things and projections, that's kind of a separate storyline, in my view. But anyway, okay. Sorry, I just thought sometimes every once in a while I should take a few minutes to kind of give you the big picture going forward. So now I'm going to cover section 7.7, which is on the structure of subspaces. So we've talked about linear independence of vectors, of sets of vectors, right? So I'm about to introduce you to the concept of independent subspaces, all right? First of all, I should probably just tell you a proposition. You know what? Well, fine. Actually, I think I'm going to follow my heart. I'm going to ignore this proposition and jump straight to the definition. So here's the definition. If you have W1, W2, WK, all right, if these are subspaces of a vector space V, and W1 plus W2 plus plus WK is equal to, and so here's the definition of this, guys. What's the definition of this sum? We've talked about the sum of two subspaces, right? So So if you add more subspaces together, you just take a sum of vectors, you know, from each subspace that you're summing. Right? So this is the sum of subspaces 1 through k, right? So suppose if this and in fact this is well, I'm debating whether to write the v here or there. I'm going to write it here. So suppose v is equal to the sum, right? So any vector in v can be written as a sum of vectors in the subspaces, all right? Then we say v is an internal direct sum of the subspaces W1 through Wk if for each x in v there exists unique x sub j in w sub j for j equals to 1, 2, all the way through k, such that x is equal to the sum of those uniquely defined pieces, x1, x2, through xk. Okay. So I'm taking that as the definition. In such a case, we denote v is equal to w1 plus circle, w2 plus circle, plus circle, wk. That's read direct sum. w1 direct sum, w2 direct sum, so forth and so on. Such subspaces are said to be independent subspaces. All right. Yeah.
What is there exists x?
Oh, there exists unique. There exists unique x sub j in wj. Now, this definition has competition because there, in fact, are 4 other equivalent statements to capture this idea. All right. The following are equivalent to the above. All right? This is my theorem 7.74. All right. So number 1, the map pi from the direct product of W1, it needs to be direct, Cartesian product, I should say. W1, Cartesian product, W2, Cartesian product, WK, to V, given by pi of x1, x2, xk, equal to x1 plus x2 plus plus xk. This map that takes the tuple, the k tuple of vectors x1 through xk into the sum of the k vectors, if this map is an isomorphism, that is one equivalent condition. Two, and this one is really independence of subspaces. So here you go, Wj intersect the sum of everything except for Wj. So W1 plus plus Wj minus 1 plus Wj plus, bless you, j plus 1 plus Ww plus Wk. So if we take the subspace Wj and we intersect it with the sum of everything except for itself, what should we get if they're independent? 0, right? So if we have this condition, and if that condition is met for each j, from j equals 1 to k, I would say condition 2 is probably what is most properly meant by independence of subspaces. All right? But again, these are equivalent statements. You can take any one of them and get the other. 3, well, 3 is the definition. Some jump to 4. 4. If beta sub j is basis for w sub j, for j equals to 1 to k, then beta equal to beta 1 union beta 2 union union beta k is what? Is a basis for V, right? In other words, they're independent subspaces. Well, it's a direct sum. It's an internal direct sum. If you can take a basis for each one of your subspaces and string them together and obtain a basis for the whole space, that also proves that the sum is an internal direct sum. Yet another way. And there is the fifth way. Again, this is 3, right? Which is my definition. The fifth way, though, is that 0 is uniquely represented. So if xi is an element, well, let me say xj is an element of wj for j equals 1 through k, and we have x1 plus x2 plus plus xk equals to 0, all right, then guess what? x1 is 0, x2 is 0, and x all the way out through xk is 0. So in other words, 0 is uniquely represented as the sum of the zeros in the subspaces. Well, yeah. Now, the full proof of this equivalent is given in my lectures on March 8th and March 10th of 2017. I'm not going to go through all that with you guys because there's no point, really. The larger point is to understand the definition, what this means, you know, W1, direct sum W2, direct sum WK, and why do we care about it? Now, it's probably worthwhile to talk. I mean, let me just open up the floor for questions. You guys have any? Is there I mean, we could try to prove one of the implication, getting one from one to the other. You could pick one. We have time for one implication, yeah?
I just had a quick question. In the notes, you read the proof of the, I guess, the very first proposition talking about, you know, the sum of the basis combined with 0, and you leave that proof to the reader.
Yeah.
And I was wondering if you're planning on doing that here, or if you could just give a little nudge.
Yeah, I could do that. Sure. The thing you're talking about is the proposition basically is that if beta j is basis for wj for j equals to 1 to k, then beta 1 union, oh, it's not that exactly. We have to deal with the pesky 0. I mean, you don't, okay, so the difference between that and this is that proposition concerns the Cartesian product of W1 through WK. Whereas whereas this, you notice that these are subspaces of a vector space V, so it's like the internal versus the external. Okay, so I got to remember how to build this silly thing. I mean, let me just drop it back here for a second. If we have beta 1 and beta 2, then we build beta as beta 1 Cartesian product with the 0 vector set unioned with the 0 vector set Cartesian product with beta 2. That gives me a basis. This is going to be a basis for W1 direct Cartesian product with W2. And that's actually proved in the notes. Most of it, anyway. I show how you can, well, okay, so what's the basis for W1, W2, WK as basis? And so I got to be, I don't know what's the right notation here, beta 1, Cartesian product with, I guess, 0, 0. I don't know. I'm not, what's the, I guess I surely have thought about a better notation when I wrote these notes. Oh, it's just awful. So beta 1, 0. It is what I feared. This. Huh? This is why I decided not to talk about this. Thank you for your question. Let's see here. But it's a reasonable question, Liam. So thank you for asking it. Anyway, this monstrosity is the basis for the Cartesian product of W1 through WK. All right. The proof, so to prove that that's the basis for W1 through W1 direct sum, excuse me, W1 Cartesian product, W2 Cartesian product, all the way through WK, we need to prove linear independence and spanning. So I think actually one calculation will more or less prove both. So what we do is just look at something like x1, x2, xk, right? Well, that is equal to the sum over x1i, v1i, sum over x2, I1, fine, I2, v2, I2, sum over xk, ik, v, k, ik, where I've introduced the notation that, for example, beta 1 has the vectors v1, comma I1, where I1 is ranging from 1 to the dimension of W1. Can't see it. Yeah, I can't see it either. What if I press this board in? No help. All right, I'm just coming up with notation for each basis and expanding each one of these x's. So this is in W1, right? This one's in W2. This one's in WK, right? But beta 1 is a basis for W1. Beta 2 is a basis for W2. So each one of these x's can be expanded into the basis of each factor, right? And then you can rewrite this actually as something like x, well, I'll use a summation notation, the sum over x1, I1 of v1, comma I1, and then zeros. And then finally you get to the sum of xk, comma ik, and then zeros, and then vk, ik here. Which shows that the basis generates everything in the Cartesian product. All right. Then you need to show linear independence of the basis. How would you do that? I won't erase it, guys. You can take a picture of it. Or Taylor, have you already? You ready? Okay, you got it. I'm going to... In the interest of not writing it again, I've zoomed in on it. There you go. That should be about at the 30-20 mark. Okay. Finally, moving along. So linear independence. For linear independence, we do what? In fact, linear independence is already set up right here. So we should set a linear combination of the basis, which is what this is, right? And we should put it equal to 0. Set it equal to 0. Then we need to study that equation and see if it doesn't imply that all of the coefficients are 0. But if this is 0, this is what? This is actually 0, 0, 0, right? So this equation implies that x1 through xk is 0, which then implies that the components of x1 through xk are all separately 0, which then gives me linear independence of this monstrous basis. That's the proof that's left to the reader, and you can see why I left it to the reader now, and why I should have continued leaving it to the reader. I was tricked. That's the worst possible question. That's the maximally awful question to ask me. Anything would have been better than that. It's evil. Genius. You're an evil genius. Okay, but listen. Before I regret today, let us move on. This is most simple, and in fact, almost all of the questions I'll ever ask you guys about are almost always concerning the case k equals to 2. So what happens with k equals to 2? We have v is equal to w1 direct sum w2 in that case, right? And so that's true if and only if what? V is equal to w1 plus w2, all right? And what? From 3, I could say, and each vector can be written uniquely as a sum of an x and a y, x1 and x2, where x1 is from w1 and x2 is from w2. That's one way I could do it, right? Or if I want to look at it in terms of independent subspaces, what does condition 2 simplify into the case k is equal to 2? Right. So one of the fundamental temptations, so a lot of linear algebra classes which have better pedagogy than mine would start with this k equals 2 case and build its way to that, right? My notes do that. And if you start with the k equals 2 case, you're very tempted to think, if I have 3 subspaces, then independence should be granted if I have what? 3 subspaces should build an internal direct sum, right? They should be independent subspaces if they're just pairwise intersections 0, right? It seems reasonable, right? But it's wrong. Let me show you why. It's pretty easy. So we need this kind of, the characterization of independent subspaces has to depend on looking at the intersection of each subspace with the sum of the rest of them. It's not enough, the generalization of what I boxed over there is not pairwise intersection. That's not what I wrote here. And let me show you why. Let's look at 3 subspaces of R2. That alone will be enough for us. Okay? So check this out. If I look at, how about this subspace, and I don't know, how about this one, right? So this is the x-axis. I'll leave it out. Now here's a notation we can use, and I will use. VR, what this means, guys, is the span of V with respect to real numbers. So more specifically, it's the set KV such that K is a real number, all right? But it's really nice to have this really nice, simple notation. So this, in that notation, is just 1, 1R. This subspace is -1, 1R. And the y-axis is just 0, 1, r. So it's easy to verify that 0, 1, r plus 1, 1, r plus minus 1, 1, r is in fact R2, right? Certainly the sum of the subspaces, if you take linear combinations of vectors along those lines through the origin, surely you get all of R2, right? We can prove that. Wouldn't be hard. And also, can you tell me what's the intersection of the lines? I mean, you know. The intersection of all my subspaces is what? Right? They only intersect at the origin. But these are not independent subspaces. And you can judge their failure any number of ways in view of theorem 7.7. I can't read. 7.74. How about the isomorphism? If we look at the isomorphism, if they were independent subspaces and we believe the theorem, it would say that R2 is isomorphic to, we call this W1, W2, W3. It would say that R2 is isomorphic to the direct sum of W1, direct product rather, of W1, W2, and W3. By the way, this is sometimes called the external direct sum, which is why I keep slipping up and calling it direct sum. All right. Internal, because W1 through WK are actually inside the vector space we're talking about. External, because we're using the W1 through WK3 in this case to build a new vector space, none of which, technically speaking, none of the subspaces are actually in that new vector space we're constructing, right? Sure, isomorphic copies of them are in there, but not the vectors, not the subspaces themselves. Anyway, this is absurd. This is three-dimensional. By the theorem I was just tricked into proving. Because if that's a basis, then you can count. The basis for the Cartesian product is the sum of the number of bases in each of the factors, which is the sum of the dimensions of the W's. So you see that we can't use pairwise intersection. Like the notion of independent subspace has to be judged by something like this, right? All right, let me get my note. Let me get the projector out here, because I can tell I am not. Well, actually, I get nervous and I give up on writing things, and I shouldn't do that. Let me not bail just yet. So. The reason, for the sake of our larger question, studying linear transformations, that these independent subspaces are interesting, is the following. So I told you guys you can't add matrices. Yes?
On the board
Oh,
over there,
stink.
in the red box, W1 intersect W2, is that
It's 0, yes. Sorry. Yeah. My brain skips sometimes. Okay, so what did I tell you at the start of the course? I said you can't add matrices that have different sizes, right? For example, if I was to tell you 1, 2, 3, 4, and then you were going to add it to 2, 2, 2, right? Then you'd be like, no, we don't do that. Well, now we do. But with this. So this is a new operation on matrices called the direct sum of matrices. And so, for example, this is 1, 2, 3, 4, 2, 2, 2. So we just put a bunch of zeros everywhere else. I suppose you could think about this operation for rectangular matrices, but I'm really only interested in square matrix, taking the direct sum of square matrices. Let me show you why. The essential theorem is this. If we have V is the direct sum. By the way, this is another notation. I equals 1 to k of Wi. So in other words, W1. All right. And if we have a linear transformation, T, from the vector space to itself, all right? And furthermore, this linear transformation plays nice with the internal direct sum for V. In particular, it is such that the linear transformation takes each one of these subspaces and sends it to itself. In other words, T of Wi is a subset of Wi for I equals to 1 to k, right? So that means that each of the subspaces is invariant, T invariant. We had a homework problem on this, right? Just for 2, really. Now I'm telling you, it works for k just the same. Then, of course, we've talked about this a little bit. TWI is a mapping from Wi to Wi. Defined how? T of x sub I, T of W sub I of x sub I is just T of xi for xi in Wi. Again, I ranging from 1 to k. So that's how we define. It's not the restriction of T, right? Because the restriction of T doesn't change the codomain. So we're both chopping the domain down to just the subspace Wi, but we're also replacing the codomain with Wi as well, which is only reasonable. Why? Why is that reasonable? Because we're assuming that the W1, the W2, all the way through Wk are invariant subspaces, which means that they map into themselves. So that makes that mapping I just wrote, the T sub Wi, well defined, right? Then the matrix of T with respect to the beta basis is equal to the direct sum of T W1 with respect to the beta 1 basis, T restricted to W2 and the codomain modified, this TW2 map anyway. I need to come up with a name for this stupid thing. I've forgotten what the name of it is. T sub WK, like that. Where the beta 1 is the basis for W1, the beta 2 is the basis for W2, the beta 3 is the basis for W3, and so forth and so on. And we're forming the basis for the whole space by concatenating, by just stringing those together in the same order, right? I'm not going to write it out. So what this says is that if you have if you have an internal, if you can write your vector space as an internal direct sum of subspaces, right? And if your linear transformation has invariance with respect to each one of those subspaces, then there exists a basis in which the matrix for the transformation just becomes this nice, pretty block diagonal thing, which is very simplifying in terms of the analysis. Let me show you some examples. And the proof of this is actually in the notes, and it's pretty simple. It's just really battling notation. The fact that you have the invariance of T with respect to each subspace, and when you just write down the coordinates, it immediately falls out. There's really not much to this theorem, except just understanding the notation. That's pretty much it. Well, this is a follow-up concerning what happens with. By the way, this is a typo right here. This is on page 336. This is supposed to be just T. There's not supposed to be a bar here. This is supposed to be T sub U. Otherwise, it wouldn't make sense. Like if I write T restricted to U, technically speaking, the codomain should be V. But the codomain here is U, as is evident from the fact that this is a square matrix. And I'm getting it. I need to go back. What page was I on? 195. So I have a few actual examples in the notes, right? For example, I know you guys can get lost in this kind of abstract jibber jabber. So here is a specific example of 3 things Cartesian product together, and here's what the basis looks like. It's like the basis for the first one with zeros tacked on, then zeros tacked onto the basis for the middle one, and then the last one with zeros tacked onto the front. That's how you make the basis for the just one at a time. That's an example. So that's one example I had to share with you. This is an important and beautiful example. Most of the things I'm going to tell you about in here going forward are about finite dimensional vector spaces. I'm assuming V is finite dimensional, right? But this example actually is infinite dimensional because what's the dimension of function space? It's infinite dimensional. But any function with a domain of the reals can be decomposed into an even and an odd function by this standard trick, right? You add f of minus x, and you subtract f of minus x after dividing by 2. So we just added 0. But this is an even function, and that is an odd function. So any function which has a domain symmetric about the origin can be decomposed into a sum of an even and an odd function. And you can prove that even and odd functions form subspaces of function space. So their sum is all functions. And their intersection is 0 because even and odd the only function which is both even and odd is the 0 function. So in fact, yeah, this is actually an example of a direct sum. The functions on R can be written as the direct sum of even and odd functions, which is kind of neat. By the way, simple example of this would be cosh and sinh. That's an example of this formula in action. That's why I always tell Calculus 1 that cosh is the even part of the exponential, but sinh is the odd part of the exponential. Likewise, this is a significant hint for any number of homework problems I'll assign in a given semester. You've maybe seen this already in your studying. This is a sneaky formula. It says any matrix can be written as a sum of a symmetric matrix and an antisymmetric matrix. By the way, the only matrix which is both symmetric and antisymmetric is the 0 matrix, and you can prove, we have looked at, in fact, in class, that symmetric matrices form a subspace. Antisymmetric matrices form a subspace of the n by n matrix vector space, right? So in fact, n by n matrices are the direct sum of symmetric and antisymmetric matrices. Also true. And there are more examples of this, like complex numbers are the direct sum of the pure real numbers and the pure imaginary numbers. This was not the example I want to show you guys, though. And you can talk about quaternions and other algebras. Here's the example. By the way, there's a typo right here. That was supposed to be 1 minus 1. Or, wait a minute. In my notation on the board, that was supposed to be 1 minus 1. Haha. So, yeah. There's the theorem I just wrote down is here. But what I wanted to show you was the example of the theorem, which was over here. So there's 2 examples. The one is a non-example. So if we look at the mapping, the derivative mapping on third-order polynomials, we get that, which gives us this matrix with respect to the standard monomial basis. And you can see that, in fact, we don't have a, if you try to, I could look at the subspace of the first 3 things, right? It's not an invariant subspace because, well, there's this pesky 3 over here, right? Well, maybe that, wait a minute, excuse me. Is something an invariant subspace here? Maybe I'm saying that wrong. Oh, I actually think that 1x squared, that's an invariant subspace, right? If you take the derivative with respect to 1x or x squared, it fits back in the span of these guys, right? But x cubed, if we differentiate that, Oh, I don't know. I'm sorry. I'm missing words here. And then this example here, the second derivative one, you notice what second derivative does? It maps x cubed to x, right? Well, 6x, and it maps x squared to 2, which is twice 1. So if you look at the span of the even powers or the span of the odd powers, those are both invariant subspaces for the twice differentiation operator. Because if you differentiate an even polynomial 2 times, you get an even polynomial. If you differentiate an odd polynomial 2 times, you get an odd polynomial. So those are invariant subspaces. And that's why when we look at the matrix, which is built as 1x squared x cubed, if in other words I put even, odd, odd, then you see we get this direct sum decomposition just like I wanted. So anyway, I will shut up. I'm sorry. Have a good break, you guys. Let me give you your test. So